scalars. Okay. Okay. So here V of f, whenever we are taking, then this V of f is called as vector space. So whenever the combination of set of vectors and field of scalars is there, to become a vector space, it has to satisfy some properties. Okay, it has to hold some axioms. That means rules will be there, no? So how how a set to become a group, it has to hold some properties as a closure, associative, additive, inverse, additive identity. Similarly, V of f to become a vector space, it has to hold some properties. Okay, so if these 1, 2, 3, 4, 5 properties are satisfied by any given set of vectors, that is V of f, then that is called as a vector space. So first unit you have the vector space is there. In that problems are also will be there, and also theorems are also there. Okay, so here vector addition will be there, and also scalar addition will be there, and also you will see zero bar. So this is called as zero vector. In vectors, we call zero. If you put on that bar, it is called as a zero vector or null vector. Null vector. Okay, in scalars only zero will be there. Okay, in scalars only zero. Okay, just zero. If you put on that bar, it is called as a zero vector. And also you may have the vector addition, means if your scalar means 2, 3, 5 like this, these are scalars. Okay, if you write them in the form of coordinate form, then it is called as vectors. That means it is equals to 2i plus 3j plus 5k. Okay, so when you add them, that is called as the addition of vectors, and also if you add the scalars, then it is called as a scalar addition. Okay. First, if you see the vector space definition, this is the main important one for all the theorems and all the units. Okay, so let f be a field, a non-empty set V is said to be a vector space over the field F. That means we'll write it as V of F if there is a binary operation plus on V. So we are using the plus binary operation on V. So first thing is it has to satisfy, first property is V comma plus. That means vectors. Here V, whatever the elements are there in the V, comma with respect to binary operation plus, it should be an abelian group. Okay, abelian group means already I have told 5 properties will be there. That means with respect to addition, it has to satisfy the closure property, associative property, additive identity, additive inverse, and also commutative law. If these 5 properties are satisfied, it is called as abelian group. And the second one is a into x plus y equals to ax plus ay. For all, means a is the element from field of scalars, and x comma y are the elements from the vectors, set of vectors. Okay, so here against the third one is a plus b into x, ax plus bx for all. A belongs to, that means here a and b belongs to field of scalars, and x is from set of vectors. So these two are called as distributive laws. Okay, if you have idea, in the groups you have seen distributive laws, left distributive law and also right distributive law will be there. So second and third are the distributive laws here. Okay, next we have fourth one, ab into x equals to a into b of x. This is the associative law with respect to multiplication. Okay, with respect to dot, with respect to multiplication, ab into x is equals to a, you have taken outside bx. Okay, so this is the associative law. These two are the distributive laws. This is the abelian group. And last fifth one is I into x equals to x. Here identity element we can take here the multiplicative identity. So one is the multiplicative identity, no? So 1 into x. So any element, if you are multiplying with 1, you will get that the same element. So here also I into x is equals to x for all x belongs to V. For all x values, if they belong to set of vectors, then Ix equals to x, where I is the multiplicative identity in field of scalars. If these 5 properties are satisfied by V of f, then it is called as a vector space. So if you'll see in your textbook, you have the first unit, vector space definition is there, page number 2. So after getting the textbook, you see page number 2, you have the vector space definition is there, and in page number 3, you have examples are there, which set of vectors means sets will become the vector spaces. So your real numbers will become the vector space over itself, means R real numbers over themselves only, they satisfy all these 5 properties and they will become the vector space. And the vector space, if you are dealing with the real numbers, then it is called as a real vector space. So if you are doing the setup with the complex numbers, it is called as a complex vector space. Okay, so almost we'll deal with the real numbers only. So almost we'll see real vector spaces only. Okay, and example second is there, R is a vector space over the set of rational numbers Q. Okay, R on Q, it satisfies the vector space conditions. Okay, so next, this is the first block. In this you have, you are not having the textbooks, that is the main problem. So first in block 1, you have unit 1 is the vector space and subspaces. This is about the block 1. In that you have unit 1. Just now I have told what is the vector spaces and subspaces. Okay. Next unit 2 is basis and dimension, and unit 3 is coefficient space. Okay. So first in unit 1, whatever the definition I have just told, that is about the vector spaces, and subspaces means similar as the subgroup. Okay. So subgroup means here we are taking any W is any set. Okay, so here V is our set of vectors. So from that we are taking another set which is called as a W, which is W is subset or equals to V. Okay, W is subset or equals to V. Means whenever any set to become as a subset of another set, it should satisfy all the properties of that one. That means this W should also satisfy all the 5 properties. Then we call it as a subspace of V. Okay, so if it is a subset means if V have some elements and W has some elements which are in V. Okay, here 1, 2, 3, 4, 5, 6 some elements are there. So on. So here if you have 3, 6, 8 some elements, okay, then we call W is the subset of V. Why? Because whatever the elements are there here, they are present in this one. So that's why this W is subset. Or sometimes you may have same 1, 2, 3, 4, 5. Then we call it as equal. If only some number elements are there, then we call it as a subset R equals to V. So when this W is called as subset or equals to V, and if this W is satisfying all the 5 properties of the vector space, then we call it as a subspace. So then we call this W as the subspace. So for showing that this W is a subspace, we need to find all the 5 properties, and if they satisfy, then only it is called as a subspace. So it is a lengthy process. So that's why they have given one necessary and sufficient condition to show that W is a subspace. If you 2 properties, if it is satisfying, then we call the W as a subspace. Okay, so no need of finding all the five properties. In the first, you have to show abelian group. Abelian group means again in that 5 properties will be there. 5 4 means 9 properties we have to show. So instead of not showing those all 9 properties, just if 2 properties are satisfied, then we can tell that W is the subspace of V. Okay, so that conditions are there in your textbook. If you see in your textbook, after this, you page number 5, you have subspaces is there. Okay, so in that subspace, first one is alpha bar comma beta bar belongs to W, implies alpha bar minus beta bar belongs to W. If this condition is satisfied, this is the first condition, and second one is A belongs to F bar. Alpha bar belongs to W, implies A alpha bar. Okay, these 2 conditions, if W, that is subset or equals to V, W is any set which is subset or equals to V. If it is satisfying the first condition, alpha comma alpha comma beta, if they belongs to set W such that alpha bar minus beta bar also. Okay, that means when you do the difference of these 2, whatever the value you are getting, that value, if it is belongs to the set W, and also if you take any element A which is belongs to field of scalars, and alpha bar is any element which is belongs to set W, and A into alpha. So when you multiply these 2, whatever the result you are getting, that result is also present in W, then W is called as a subspace of V. Okay, this is called as a necessary and sufficient condition for a subspace. If these 2 properties, means no need of showing all the 9 properties. If these 2 are, they are satisfied, then it is called as a subspace. And you have one theorem also in your textbook. So in that theorem, you have the condition is A comma B if they belongs to F, and alpha bar comma beta bar belongs to W, then A into alpha bar plus B into beta bar belongs to W. So this is also third one. This is also, means here 2 we are doing. Instead of 2, if this last third property, if it is only satisfied, then also W is called as a subspace of V. Okay, first thing is 9 properties, if they are satisfied, if you show, then also it is called as a subspace. If these 2 properties are satisfied, then also W is called as a subspace. If only the single property, if you show it is satisfying, then also we call it as W as a subspace. Okay, if you do some problems, then you can understand the concept of what is subspace. So theorem is there. This is the necessary and sufficient condition, okay, to show that W is a subspace. So the proof of the theorem is there, and whatever the vector spaces is there, this definition they will ask for 5 marks. Define vector space and give some examples. And even subspaces only definition you will get, but whatever the theorem is there, A alpha plus B beta belongs to W, you will get for the 10 marks questions. Okay, so first unit you may have subspaces, in that you will get the 10 marks questions to show that any given set is a subspace. Okay, so page number 8 you have some theorems are there, page number 8 and 9. Okay, so in this, the concept of vector space and example, you will get 5 marks, and this is the 10 marks question. Okay, so or else if you are not getting here any 10 marks question, you will get in basis and dimension or coefficient space. Okay, so next if you go to the unit 2, it is the basis and dimensions. So here basis, what is the basis and what is the dimension you have. So in second unit, you have the concept of linear combination So we can represent it as L dot C, that is linear combination of vectors. So if it in the form of A1 x1 plus A2 x2 so on up till AN xn. Okay. So that means you are taking the scalars x1, x2, x3 up till xn, and also you are taking the vectors as a1, a2, a3. So if you write them as the combination, that is the a1 into x1 plus a2 into x2 and up so on up till you will get an into xn. So whenever you can write like this, it is called as a linear combination. Okay. So from the linear combination only you have the linearly independent vectors. Independent vectors and also linearly dependent vectors. So if you see, this is the shortcut Li and this is the Ld. Okay. So first you should know what is linear combination. From the linear combination only we will find what is linearly independent, what is linearly dependent. Okay. So when you get like this linear combination, if here all the coefficients, that is a1, a2, a3, if they are equals to, that is a1 equals to a2 equals to a3 equals to so on, if you after solving this linear combination, if you are getting a1 value, a2 value, a3 value, all zeros, then we call that as linearly independent vectors. Okay. So any one linearly dependent means from this any one, that means any of one, if you are not getting zero, you may get a2, a3 values as zeros, but you may not get a1 as not zero. So such type of vectors are called as linearly dependent vectors. Okay. If all a1, a2, a3 values, if all you're getting as zero, then it is called as a linear independent vectors. Any one of vector, if you are not getting as non-zero, then that is called as linearly dependent vectors. Okay. So this is the concept of linear combination, independent, linearly independent and linearly dependent vectors. So why I am telling this, because basis is related with linearly independent. Okay. So linearly independent vectors. If you see the basis definition in second unit. So first thing is SC is any subset. Okay. Yes, you have any set such that it is a non-empty set, then is T subset or equals to. So here we are taking the basis definition. Okay. That is SC subset or equals to vector space V of F. First condition is SC is Li. That means S should be linearly independent. Okay. So to become any set S as the basis, the first condition is S is Li and second one L of S equals to V. Okay. This is called as L of S equals to V. This is called as linear span. Linear span. Okay. Linear span of S is, should be equal to V. V means here set of vectors. That means whatever the elements are there in the V set of vectors, that all elements should form the linear combination with respect to set S. Linear span definition is that each and every element of set of vectors, it should form the linear combination with respect to set S. Then L of S is equals to V. That is called as a linear span. So if these two conditions are satisfied, then this S is called as a basis of vector space. Okay. So when you take 1, 2, 3 elements, V is a set of vectors. So many vectors are there in that. So if you take first, alpha is one of the set. So with that you are making the linear combination with respect to S, and also with beta, and also with gamma, and also with delta, such that you are taking all them and you are forming the linear combination. Then that L of S is equals to V, set of vectors. Okay. So from this basis, it is related with dimension. Dimension is nothing but number of elements present in the basis. Okay, so the elements you're taking alpha, beta, gamma, after that delta, x, y, z, so on, all the values you are taking as a set S. So you're taking S as alpha, beta, gamma, delta, and so on, like this. So these are all the set of vectors. They are forming with the set S. So these elements present in the basis, the number of elements present in the basis is called as a dimension, and we represent as that is dim. Okay, dim of V of vector. So if you have here, if it is a finite set, so if you take only these up till delta, so how many are there? 1, 2, 3, 4. So of this V, so dimension of V is equals to 4 here. So the number of elements present in the set of the basis set, the number of elements are present that are called as dimension of V is equals to the elements. So basis and dimension, on this also you have some theorems are there. Okay, so linear algebra almost theoretically only will be there. All the problems rarely you will get, that is in block 3 and block 4 you will get the problems. In this first and second block compulsory you will get all the theorems, only small 5 marks questions you will have. Okay, 16th page number you have basis and dimensions, and 17th page number you have the theorem. It is the 10 marks theorem. Okay, 2.3.3. okay, 3.3. 2.3.3. this is the 10 marks theorem in basis and dimensions. So small problems also will give, they'll give you some basis, and they'll ask for even 1 mark questions, multiple choice or anywhere the set will be given, he will ask what is the dimension of that one. Okay, so dimension means here number of elements present in the basis. Okay, so next third we have quotient space. Okay, so how you have in groups, rings, quotient group is there, quotient ring is there. Similarly you have quotient space. So before the quotient space, if you have idea, we have seen the coset, right coset and also left coset in groups. Okay, left coset and right coset. Similarly in rings we have seen ideals, that is a left ideal and right ideal. Similarly in vector spaces you have quotient space. So like this it will be there, V by W. Okay, representation of quotient space will be in the form of V by W. So it is defined some way. So the definition will be given for the quotient space. So with the help of the definition, you have the theorems are there on quotient space. Okay. So if you have test book, you have on page number 25. On page number 25, you have V by W, that is V quotient of W is defined as X plus W such that it is equals to X plus W such that X belongs to V. Okay. And some other thing is also there. You see the definition. So while going through the unit, we'll see. So this is the definition of the quotient space. So with respect of, we'll write it as V quotient of W. It is defined as X plus W such that X belongs to set of vectors V. So in this also you have the theorems are there. Page number 25 you have 3.3.1 and 26 page number 3.3.3. It is a very important one, 10 marks questions, and this is a regularly asked one. Okay, 3.3.3 and also 3.4.1. Almost they are interrelated to each other. Slight changes will be there. So 2 10 marks questions, any one you will get. Okay, so vector space 5 marks. Subspaces also you have the chance of 5 marks only, and in basis and dimension you have the theorem of 10 marks, and quotient space you have the theorem on 10 marks. So 2 10 marks questions from 2 and 3, 1 5 marks question from vector spaces. From here you may get any one 5 marks questions. Okay, so this is about unit 1 2 3 in block 1. Next we will see the block 2. So block 2 is linear transformation is there in that unit 4. Linear transformation. And fifth one is rank and nullity. And the sixth one is matrix of linear transformation. Okay. So first unit 4 is linear transformation. Linear transformation is same as the homomorphism of groups or homomorphism of rings. Okay. Homomorphism of groups or else rings. Same, whatever the conditions are there for any group to become as a homomorphism, we have seen 1 1 and on 2 will be there, and you will have the mapping in between of them. So such type of whatever the homomorphism is there will deal with the linear transformation. So linear transformation, you have the definition is there. So linear transformation means it's in between of two any vectors, that is u of f and also v of f. Linear transformation will be for u of f and also v of f. If we'll take the mapping u and also v, this is the alpha, f of alpha, and if we take beta, f of beta bar, and if it is alpha plus beta, f of alpha bar plus beta bar. So if we'll take like this mapping, so here and here will represent the linear transformation with capital T. Capital T is any function which is mapping from u to v. Okay, linear transformation here T, it is any function which is mapping from u to v, such that if it is satisfying the condition, that is this is the domain. In domain you are having the elements as alpha bar, beta bar, and alpha bar plus beta bar. When it is mapping with v, you will get f of alpha bar and f of beta bar. So the main thing is alpha bar plus beta bar is equals to f of alpha bar plus beta bar is equals to okay, f of alpha bar plus beta bar equals to f of alpha bar plus f of beta bar. So whenever you write like this is called as a homomorphism of this one. F of alpha bar plus beta bar equals to, that means you are separating this one, f of alpha bar plus f of beta bar. So from this we will get the definition of the linear transformation. Okay. So for any set to become a linear transformation, it has to satisfy the two condition is there. First one is the f of alpha bar plus beta bar equals to f of alpha bar plus f of beta bar. Another one is f of a into alpha bar equals to these two. Okay. If any set T mapping from u to v, if it is satisfying this first one and the second condition, then it is called as a linear transformation. Okay. First one is f of alpha bar plus beta bar equals to f of alpha bar plus beta bar. Second one is f of a into alpha bar equals to, if we take a outside, a into f of alpha bar. If these two are conditions satisfied by T, then it is called as a linear transformation. Okay. So this is about the unit 4. Next we have rank and nullity. So rank and nullity in that will represent with R of T. It is called as rank, and nullity mean n of T. Okay. Rank means will represent with R of T and nullity means will represent with n of T. Okay. So rank and nullity are nothing but the range of the linear transformation. Okay. Range means here whatever the images you are getting. If you have the idea about the functions, in that you know what is a domain, codomain, and also range. Range means if whatever the codomain is there, it is having the image in U elements. if you take here x, y, z, and here you are not having the any images. Here t, u, t, f, small f, any elements you take, only all f of alpha, f of beta, f of alpha plus beta, these only you are having the images here, but x, y, z you are not having here the images. So when you write the range, we'll write only these three as the range. When you write that whatever the set in the form of the range elements, that is called as a range of the linear transformation. Okay, range means codomain elements which have image in with the domain elements. The other elements t, f, or something z like that, whatever the elements are there, they are not having the images in u. Okay, that is called as a range of the linear transformation. Okay. And if you have this, you see here u and v, you have no. So u and this is v. So in this, whatever the vector will be there, you will have zero vector, zero bar. So if you have zero bar and cap, okay, this is called as a zero vector. That is zero, just on that if you take the bar, and if you put zero bar and that whatever the small cap is there, that is called as zero bar cap. So then we call it as a null space, null vector. Okay, that is represent as n of t. Okay, this zero vector is called as a null vector, or else will represent as n of t. Okay, so these rank and nullity, on that you have theorem is there. Okay, rank and nullity, it is a fifth unit. So that is also 10 marks questions are there. In this only you have a fundamental theorem of vector spaces is there. So in that you will get the that is a homomorphism image will be there. If it is 1, 1 and on 2 and also homomorphism, then it will satisfying the condition of fundamental theorem of homomorphism. Okay, this is about the block 2. So block 1, block 2, almost they are the all theorems will be there. And last 60 unit you have no matrix of linear transformation, means in that you have the definition of, if you write whatever the linear transformation in the form of a matrix, then it is called as a matrix of linear transformation. Even in 60 unit only you have the concept of linear operators. Okay, so linear operators, you may get one problem in the last 60 unit, you have problems are there, you will get for the 5 marks. That is finding the matrix, any vectors will be given. So from that, after converting, you write the vectors in the form of a matrix, that is called as matrix of linear transformation. So you have the 5 marks question, or linear operators is their basis with the respective of the basis. So that is also a 5 marks question. Problems, if you get those two problems, you may get any one. And theorem is there, means theorem is the fundamental theorem of homomorphism of vector spaces will be there. Okay, next block 3 we have. And even one more definition for the linear algebra is that it is even the study of linear equations. Linear equations means if you have the idea about matrices, so they will be in the form of like this: a11x, if you take a11y plus a3z. Okay, b1x b2y plus b3z equals to 0, and c1x plus c2y plus c3z equals to 0. Okay, so these whatever the equations are, they called, even linear algebra is also called as a study of the linear equations. Okay, so even whatever these are there, these are in the form of linear combination of vectors also. Okay, so if on the right hand side, if you have zeros, then we call it as a homogeneous linear equation. Okay, that is a1x plus a2y plus a3z equals to 0, or b1x b2y plus b3z equals to 0, c1 and this one. So if you have on the right hand side zeros are there, it is called as a homogeneous linear equations. Okay, so if you have here some values, that is 4, 5, 6, or you can take it as d1, d2, dt. Okay, so if you have the like this any numbers in problems, you will get the numbers. If like this, when you define d1, d2, d3, so if instead of zeros, if you have d1, d2, d3, it is called as non-homogeneous linear equations. Okay, non-homogeneous linear equations. So block 3 is in that unit 7. It is elementary transformation. Elementary transformations. Unit 8 is system of linear equations. And unit 9 is characteristic roots and characteristic vectors. And in this only you have Cayley-Hamilton theorem. Okay, Cayley-Hamilton theorem. So the block 3 and block 4 are somewhat problematic while compared to 1 and 2. Okay, so easily you can score marks in 3 and 4 blocks. So in this only you will have all the problems. Even unit 7, unit 8 and 9. These are the all problematic one. In unit 7, it is the elementary transformation. Okay, those who have completed the intermediate, you have the idea about elementary transformation for finding the rank of a matrix. Okay, for conversion of any 4 by 4 matrix to the 3 by 3 matrix or 5 by 4 or 4 by 5 matrix orders. Okay, if you convert them into to find the rank of the matrix, we'll use the term elementary transformation, that is row operations and also column operations, and we'll convert the given matrix into the identity matrix to form the normal form. Okay, so to find the main thing is elementary transformations. You'll find for rank of the matrix. Okay, so one theorem is there, elementary transformations, that is a elementary transformation do not alter the rank of the matrix. This is the 10 marks theorem. Okay, compulsory you will get in any one series. You have the series, no? That is A series will be there, B series and also C series. So in that any one you will get the 10 marks question as this theorem. That is the elementary transformation do not alter the rank of a matrix. So when you apply the elementary transformations, then the rank of the matrix will not change. Okay, so that you have the proof of the theorem is there, that you have in unit 7. Okay, and in unit 7 only conversion of any given matrix into normal form. Normal form means if you think it is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, like this any matrix is there. If you are converting this matrix into any identity matrix, you may get like this also. So whatever the elements are there, you have to convert them like this. 1, 0, 0, 0, 1, 0, 0. You may have, this is the identity matrix of 3 by 3. Okay. This is the identity matrix. Up till here, it is the identity matrix of 3 by 3. In some cases, you may get the identity matrix of 2 by 2 also. So when you convert the given matrix into like this, it is called as a normal form of a matrix. And by this, we can find if identity matrix, it is 2 by 2, then the rank of the matrix is 2. If you are converting the given matrix into 3 by 3 identity matrix, the rank of the matrix is 3. Okay. So conversion of the given matrix into normal form is to know the rank of the matrix. Okay. That problem you will have, you may get in some cases, they will ask for 10 marks or as 5 marks question. Okay. In unit 7, finding the rank of the matrix only is there. And one more is echelon form will be there. This is also for finding the rank of the matrix only. Okay. So you have to convert the given matrix into echelon form. Number of non-zero rows are there, if 2 non-zero rows are there, then the matrix rank is 2. If 3 non-zero rows are there, then the rank of the matrix is 3. Okay. So this you have in unit 7, and unit 8 you have system of linear equations, whatever I have told this one. So you will find the system of linear equations for homogeneous and for non-homogeneous. So the main thing is, for finding the system of linear equations, you have to find what is the rank, and you have to find x, y, z values for homogeneous and for non-homogeneous. So this also, these problems you may have the chance of getting even for 5 marks. If it is a homogeneous, 10 marks you may get for non-homogeneous one. So in this only you have to find the Cayley-Hamilton theorem is there in unit 9. Okay. So the problems will be on homogeneous and non-homogeneous and also echelon form. Okay. 3 problems are there. In that, any one problem for 5 or 10 marks you will get. Last one is characteristic roots and characteristic vectors and Cayley-Hamilton theorem. Okay. So 10 marks theorem you will get for Cayley-Hamilton theorem. So Cayley-Hamilton theorem statement you have to write, and you have to write the proof. Okay. Statement will be the every square matrix satisfies its characteristic equation. Every square matrix satisfies its characteristic equation. That is the statement of Cayley-Hamilton theorem. For that you have the proof. So that is the 10 marks question. And if you get in one series Cayley-Hamilton theorem proof, you will get a verification of the Cayley-Hamilton theorem problems are there. Okay. So that you will get in another series 10 marks question. Okay. So characteristic roots and vectors, that is only the 5 marks question. So here first thing is characteristic equation will be there, that will be in the form of A minus delta I. This is called as a determinant. Determinant of A minus delta I equals to 0. It is called as characteristic equation. Okay. So this, from the characteristic equation, A is the given matrix here, I is the identity matrix. When you do the subtraction of this one and when you find the determinant, you will get the lambda value, some lambda values that are called as characteristic roots. Whatever the lambda values you are getting, those are called as characteristic roots. And when you substitute this lambda value in given this, whatever the matrix, when you substitute that, whatever values you are getting, those are called as characteristic vectors. Okay. So if it is a 5 marks question, they will ask what are the characteristic roots of the given matrix, or else what are the characteristic vectors. This means only up till here it's enough. But when he is asking vectors, means lambda values are nothing but the roots here. If you are getting 1, 2 value as the lambda values, you have to substitute this 1, 2 here, and then we have to find the values. That values are called as a characteristic vectors. So these two are the 5 marks question. This is the 10 marks question. So 10 marks question, this one, and compulsory here. So here you may or may not get the 10 marks question, but system of linear equation 1 5 marks problem compulsory you will get. Okay. So verification of Cayley-Hamilton theorem and proof of Cayley-Hamilton theorem 10 marks question, and elementary transformation normal form or the theorem itself is the 10 marks question. So this is about block 3, and last one we have block 4 we have. So this is about inner product space. So it is somewhat different from this one. Quadratic form. Unit 11 is okay. This is the last block we have. that is a block 4, unit 10, 11, 12. So this is the quadratic form. So quadratic form is nothing but whatever the vectors will be, that is a matrix will be given. That matrix when you write in the form of Q of x equals to, that is x1 square plus 2 x1 x2 plus x2 square plus 3x1 x2, or else you will have x1 x3. Okay, so like this, when you're writing in this form, this is called as a quadratic form. When you write this one only in the form of like this matrix, it is called as matrix form. So x1 square means here 1, x2 square means 1, x3 is not there, 0, x1 x2. So you will get here 1 1 x3 3 by 2, and you will get here 3 by 2. So your values are not there, so 0 0. So while seeing the problems, we'll see this procedure. Okay, so writing like this as a matrix form, this is called as a matrix form. If whatever the elements are there, if you write them as like this, then it is called as a quadratic form. So here you will have only the 5 marks question in this quadratic forms, and one you may get the any given matrix form you have to write in quadratic form, or quadratic form you have to write in matrix form. That is a 5 marks question. So in this only they will ask quadratic form whether show that it is a negative definite or positive definite. Okay, that problems are there in quadratic form. So only 5 marks question you will get from the unit 10. Only one 5 marks question you will get from the unit 10. So whenever you go to 11 and 12, compulsory from this 10 marks and for this 10 marks. So here you have the theorems, but theorems are somewhat easy compared to block 1 and block 2. These two somewhat theorems are easy. Okay, in this you have the definition of what is inner product space, and Schwarz inequality theorem is there. Schwarz inequality theorem is there, and parallelogram theorem is there in this. Parallelogram theorem and triangle theorem is there, triangle inequality. Okay. And last 12th unit is the orthogonality and Gram-Schmidt orthogonalization. This is the 10 marks theorem you will have. Compulsory you will get this one. This theorem is there, state and prove the Gram-Schmidt orthogonalization. See page number 132, you have Gram-Schmidt orthogonalization process. This is the compulsory 10 marks. And here you will get the Schwarz inequality theorem. This is also 10 marks one. So from 11 and 12 to 10 marks questions you will get. So this is the 10 marks. And parallelogram theorem, this is the 5 marks. And even triangle inequality is there. This is also 5 marks. Okay. So these are about the 4 blocks. And I have told what are the important questions also you are getting from the 4 blocks. So try to whatever the topics we can cover in the 4 classes, I'll try to complete those. We'll see almost 3rd and 4th block. Starting whatever the introduction I have told for the vector space, basis and dimension. If we have time, we'll see the problems on that, which you will get for 5 marks questions. Theorem I'll give the from the textbook, you try to practice all the theorems. Okay, from 3 and 4 you will have the problems, so easily you can score almost maximum marks from the 3rd and 4th block. Why? Because they are the problems. If you have completed already the intermediate, you have the idea about the rank of the matrix, and Cayley-Hamilton theorem you have in intermediate also. Okay, so proof of that one. And also these 2 theorems are also easy. Schwarz inequality and also Gram-Schmidt orthogonalization process theorem is there. No, on this problem is also there. Okay, and these 2 theorems also very small and easy one. Okay, so from 3rd and 4th block, we try to complete the maximum 10 marks questions and also 5 marks question. And even from block 1 and block 2, whatever the problematic are there, we'll see the problematic one. So if we'll go depth into the theorems, one class only one theorem we may complete. So all the classes will be completed. So that's why we are not going into the theorems. If you'll get the textbooks, I'll give all the important theorems. If you know the definitions, I'll try to tell the definitions how. So through the definitions only, you can do the proof of the theorems. Okay. So after completion of the 5th class, we'll go to the 3-dimensional geometry. So 3-dimensional geometry, it is all the problematic one only. In that very rare two or three theorems are there, but all are solving the problems only. Okay. So we'll see tomorrow class. We'll start starting vector, whatever the vector space definition is there. Through that we'll see some properties are there. How they are satisfied we'll see, and I will go to the problematic of block 3 and block 4. Okay.